Hi, thank you for joining this session or recording or whatever it'll be. My name is Ruben Balanya. I'm a customer success engineer at TechMax, and today I'm going to take you through a simple demonstration of an authentication overflow attack. So if we just dive right into it, first I'm going to take you through the simple source code to show and demonstrate how an authentication buffer overflow attack can occur. So if you just input into the console, nano auth overflow.c. So we're going to quickly go through the source code and take a look at it to see how it operates using the nano command. And this is just simply it, the source code for the buffer overflow. So first, we include the necessary libraries to load up the required operating system functions necessary for the program to work. Next, we move on to the check authentication function, which takes in a string, which is the password. It initializes an auth flag to set it to the variable 0. And also it initializes a password buffer of 16 characters. Now, this is important as this is where the overflow will happen. Next, we move on to the line for the string copy, which copies the argument password and puts it into the password buffer. Next, we have a string comparance. So if the data that is in the password buffer is equal to checkmarks, the 0 stands for equality. If it's equal, the auth flag will be set to 1. Else, there's not really an else, but if they're not equal, the auth flag will remain 0. And then the function will return the auth flag. Next, we move on to the main function, which takes in the input from the user as well as the program name and displays in its arguments the number of arguments that have been input into the program. If the arguments are less than 2, then the program will just print how to use the program in general. If the arguments are more than 2, the program will just continue into the check authentication function. So the check authentication function takes in the second argument, which will be the required password that you put into the program. That is argv1. And this is the key part here. If it returns anything that is not 0, it will print access granted. Else, if it returns 0, it will print access denied. So ideally, based on the program, if you input checkmarks, it'll grant you permission into the system. And if you input anything else, it'll tell you, no, you can't enter the system. So let's try and put this into practice. Okay, so now we are going to run the command. As you can see, if you put in the test as the password, then access is denied. And if we put in checkmarks as the password, access is granted. Easy as that. However, there is a vulnerability in the source code logic, in which if you put in a long enough string of characters without causing a segmentation flow to the operating system, you'll be granted access as shown below. Okay, it still grants a segmentation fault, but as you can see, we've been granted access into the system and the password is not checkmarks. So how does this occur? I'm sure many of you will have already noticed by now that there is a buffer overflow attack in this program and also programming logic. But let's take a look at the GDB. Let's take a look at the program using the GDB debugger to see what's going on under the hood. Okay, so inside the GDB, and you can access the GDB by simply inputting the command gdb. The dash q negates the welcome banner, so it's more cleaner. And the program you want to inspect the memory of. So first, we're going to list off the source code of the program by simply uh, inputting lists. And this is the section of the program of which we want to focus on. Next, we're going to put breakpoints at certain areas of the program in order to inspect the memory and see why a random string of characters enables one to gain access into the system. So first, we're going to put a breakpoint at the string copy command. Next, we're going to put a breakpoint just before the execution of the return auth flag. Having put those specific breakpoints, we're going to run the program using the string of characters that we whipped up in order to gain access into the system. So first, it pauses at the first breakpoint before the password argument is put into the password buffer. So we're just going to inspect the memories of both the password buffer and the auth flag. So as you can see, nothing has been set yet into the password buffer, as the command to set the password buffer as password has not been input yet. Let's take a look at the auth flag. And as you can see, the memory location that holds the auth flag is also set to 0. The command X followed by an S stands for examine the memory and examine the string that is in password buffer. For X, it stands for examine the memory as hexadecimal digits. So we've seen how the memory looks like. And we can also, since the password buffer sits on top of the auth flag will have a higher memory address. So you can use a print function to print the distance between the start of the password buffer and where the auth flag is. We can see the distance is 28 bytes. And if we just print the password buffer as a long list of memory, we can see where specifically the auth flag will be relative to the password buffer. So for this, it's to examine the 16 hexadecimal words of the password buffer. So as you can see, the distance between the password buffer and the auth flag is 28 bytes. This is 56 digits, hexadecimal digits. So the start of the auth flag will be here specifically. As if you take a count from this first area where the password buffer starts, going from left to right, top to down, the distance between here and here will be 56 hexadecimal digits. Next, we can continue to run the command to see what the auth flag will hold after the password has been copied into the password buffer. So if we continue with the program, we see the breakpoint has been put where the return auth flag is, just before it's returned to the main program. Again, we'll take a look at the memories for the password buffer and the auth flag. So as we can see if we examine the password buffer, the memory as a string, we can see A has been repeated 30 times. And if we examine the auth flag, we can see that it's been set to the variable, the hexadecimal digit 41. But how has this occurred? Let's take a look. So if we print out the password buffer again, this time you'll notice a difference between the memory segments here and the memory segments here. As you can see, when we put the random list of the character A, the character A in hexadecimal is 41, and we put a rather huge amount of it, more than the buffer could handle. So it overflowed into the auth flag variable. Remember when I said the auth flag variable can be found here? So you can see some of the 41s, which are just the A's, have overflown into the auth flag variable here. And the reason why it looks like this is due to the little endian nature of the system. So instead of starting with 41 at the start, it prints out the zeros first and prints out the 41s at the back. So you can see two A digits overflowed into the auth flag variable. Okay, and then next we can examine the auth flag as 4 units, 4 characters, each 1 byte. So you can see in the auth flag, which is here, the first 41 corresponds to this A. The second 41 corresponds to this A. This 0 corresponds to the 0 here. And the last set of zeros correspond to the last set of zeros there. If we take a look at the auth flag in decimal, which is what the program will look at it as, we can see that we get the variable, the auth flag has been set to the decimal digit, 16,705. So remember when I told you the program has a programming flaw in it? Hmm. Let's go back to the source code and see. So for this check, if check authentication, this only checks if something is either 0 or not 0. It doesn't matter if it's 1 or 1,000. As long as it's not 0, it'll give access to the system. So this is where, as a developer, you might go through to check your code for programming logic like these, or have peer reviews, or even give some of your colleagues a chance to take a look at your work in order to validate the code that you've written, to make sure that it's okay, it's logically sound, and it's secure before even testing, before development, in an effort to reduce the manpower, the time it takes, the effort of correcting code once it's finally done. You can catch things like these easily during design and development of the code. So if we just continue with the program, we can see, yeah, access was granted. And this was a result of the auth of data from the password buffer overflowing into the auth flag and changing the auth flag from 0, as it should have been, to an arbitrary random number. So these are the types of techniques and tricks that malicious actors usually use to take control of your systems. Yeah, this was just a short session to demonstrate how buffer overflows attack from a low level view. And thank you for joining in and tuning in to the session.